Hi all and good morning again. So let's continue our class. From last week, we have learned how to program the microprocessor already. We have learned how to write the program. And today we will continue uh, on writing a more advanced program where we will look at what is called a subroutine and also the stack and also the subroutine. Yeah. So first is the stack, right? So as we have known uh, that microprocessor, the hardware resources in the microprocessor, the register, the ALU, the control circuit, and uh, are very limited. Yeah. So we have only 15 registers. So if you want to manipulate a data, sometimes we need to keep the data and or we have huge of data. So sometimes we want to keep some of the data and process another data and want to use the data that we processed previously again. So we need to keep that data, right? So the way to keep the data is to put in the memory. Okay, and one of the very efficient way to store the data temporarily in the memory is using what we call the stack. Yeah, stack. So the concept of stack is like this. So this is the memory, part of the memory, and we can actually define that area of memory as stack. So how the stack work? All right. So what we do in the stack is that we can insert the data into the stack, and the process of inserting the data into the stack is called push. Push. And when we push the data into the stack, it works like this. LIFO, or last in first out, means that if the data here is pushed into the stack, it will be the first data it will be stored at the bottom of the stack, and this is called the bottom of the stack. All right, and when you push the next data into the stack, it will be at the next level of the bottom. So for example, this is the first data, and you push again the data, the second data will be here, the third data will be here, and the fourth and so on data. Yeah, so it is stored in the stack like that. So that is why it is called a stack. And when we want to get the data back from the memory, so the process is called pop. Pop. So when you want to pop the data from the stack, so the first data that will be popped from the stack is the one that is on the top of the stack. All right. So for example, this one is the last data that enter the stack. So when we pop, this one will go first. That's why we call it last in, first out, or first in, last out, right? So that is how the stack works. This is very useful in sorting the data, in keeping the data temporarily. When we have huge of data to be processed, and sometimes we have processed that, and we want to use that data again, but before that we need to process another data. So the previous data we need to keep in the stack, and when we want to use again, we can pop it out. So that is how we use the stack. So in program, how to define and write the program to use the stack. So this is the example of the program how to pop the data, how to push the data into the stack, and how to pop the data from the stack, right? And again, before that, here we call bottom of the stack, and the last data, all right, the address of the last data that enter the stack is called top of the stack, or TOS in short. Yeah, bottom of the stack is BOS, yeah? Bottom of stack. So this is how we use the stack, yeah, in ARM microprocessor. So first is to uh, to define the stack area, right? This is how we define the stack area, right? For example, the stack area is defined at this address in the memory. Okay, so if you define the stack area, you need to load that data into the SP. Yes, SP register. Remember what is SP register? SP register is the stack pointer. Yeah, the stack pointer. So for this, we need to go back to chapter 2, where uh, look back at the programmer model, right? So let's go back again to chapter 2. Where we have this R13, which is the stack pointer. So this is the register that keep or hold the address of the top of the stack, TOS, the stack pointer. So it will always point to the top of the stack. Right? So in this case, we need to define in our program where is our top of the stack, or the address of the stack. So in this case, we define at this memory location, and we need to load into the SP. The SP is the stack pointer. You can define any location in the memory that is writable, that is writable for the stack. All right, but if in your program you not define the address of the stack, it will be assigned automatically by the compiler, right? So in this case, it is assigned by us as a programmer. So this is the stack address, and for example, this is the data that we want to save in the stack, and the data is in R0 and R1, right? So to push the data into the stack is just using push R0, and we have curly bracket R0. So the content of R0 will go to the stack, and push R1, the content of R1 will go to the stack at the top. So here R1 will be in the at the top of the stack, and this is how we pop. So when we pop, so this is the first data to be popped from the stack. Means that the data that is from R1. So we will save in R2, and when we pop again, we will pop the next data, which is this one. So when we use pop or push, so the operation is in 32-bit. All right, so the data is in 32-bit. So let's look at this example. How is this work? Right. So when we define the stack address and put in the SP, or load into the SP register like this, so the SP will get this address, right? Because STKAD is Yeah, we assign this value to stkadd and use equate assembler directive. So this is not uh, instruction set. Yeah, EQU is not instruction set. Remember, EQU is assembly directive. So we assign this value to stkadd. So when we used here stkadd means that this value, right, put into SP. So when we execute this code, we will have this value in SP, right? And when we use LDR R0 means that we load the address. This is value and to R0, and when we load again this value into R1, so we have this in R1. And when we do this, what happens is that the part of the memory from 2000 is the base state stack address, stack base address. So this is base address of the stack, right? Means that when we push the data, for example, when we push R0, so the value inside R0 will go to this. Okay, so this is how it's work. It is stored not here, yeah. It is stored like this. This is the things that you need to remember. When this is our top of the stack, so it will put here, and this memory is drawn in 32-bit in size. Actually, in the memory, remember, we actually draw in 8-bit format, right? So let's look at this. So in the memory, actually we have something like this, and the base of the stack is, or bottom of the stack, yeah, is the address is, and if we draw in 8-bit format, we will have the next one is and we have FE, and we have FD, and we have FC, and the next one will be FB, and so on. All right. So this is the next means that it's backward, yeah. -1, -1, -1, -1. All right. So the address 0 will be at the top here. Okay. So the data is this 1, 2, 3, 4, 5, 6, 7, 7, 8. All right. So in this case, it is drawn in 32-bit. So in 8-bit, it should be like this. Should be 1, 2, 3, 4, 5, 6, 7, 8. All right, all 32 bit will be pushed into the memory like this, and the top of the stack is now here, 200000 FC. That's why we have this 200000 FC, the top of the stack, when we push R0 into the stack, right? So remember, when we push the data into the stack, and this will be our base address, and the data will be stored like this, right? 1 2 3 4 5 6 7 8 in the memory. And next, when we push again art1, so the value of art1 will go to the stack here, and this will be the top of the stack now, right? Again, it is stored like this: 1A, 2A, 3A, 4A, 1A, 2A, 3A, 4, 4A in the stack when you push art1 into the stack. And when you want to retrieve the data back, means that you want to pop the data out of the stack. So when you pop R2, so R2 will be this, or get the data from the top of the stack here. This is the data. It will go to R2, and now the top of the stack will be FC, here. And when you pop again, so this data will go to R2, and now this stack, the bottom of the stack or stack base address is back to 20000100, means that now the stack is empty. All right, and let's look at the SP when you push. So for example, when you push R0, the first data into the stack, so SP will be updated with the TOS value. See, FC, and when you push again, F8, and when you pop, so R2 will get SP will get this TOS again, FC, and when you pop again here, right? So this is how you push and pop the data, or how you use the stack in microprocessor. All right. So maybe we can look at program example. All right, when we run in kill and see what happened in the memory. All right, so let's open kill mu vision or microvision. So let's have a look at this. So I have this program, exactly the same with the lecture note here. Can try to see when we execute this program, what happened to the memory and the content of the register. The memory, let's set to D0 because our base stack, base of the stack is 100, so we try to get this is better, 100. So this is the our TOS, yeah, before we execute the program. So let's run the program. Okay, so this is the value before we execute the LDR SP stack AD. So inside LR we have 3C5, which is the initial value of the stack. This one, which is the initial value of the stack, but we want to have a value or the stack base address that we define ourselves. So let's run this. So we will have this value in SP. Now when we execute this instruction, next the instruction to be executed is to load R0 with this value. So we have this value in R0, and then we put this value in R1, and we have in R1 here. And now we want to push R0. Yeah, this is the instruction to be executed. Yeah, push R0. Yeah, push R0. So our R0 is here, and remember this is our stack. Yeah, this is the top. This is the top of the stack, and the address that we are looking for should be here. All right, this is 2000000FF, and this is FE, FD, FC here. All right, so let's run this instruction, and we push already the value, the first value from R0 into the stack. So we will see in the stack here we have 1 2 3 4 5 6 7 8. All right, and now the top of the stack is here, and this is the address of this. Yeah, FC. How do we know that this is FC? So we need to look at this. So this is the address of this F0 here. All right, this is F1, F2, F3, F4, 5, 6, 7, 8, 9, A. So this is FA, this is FB, so this is FC here. 200 FC is here, right? And let's now execute the next push, push R1. So this is push R1. So how do we know that we want to execute this? Look at this arrow. Yeah, this yellow arrow. This means that the next instruction to be executed. So when we press this button, means that this one will be executed. So when we press, see the arrow will go to the next one, yeah, to the next to be executed, which is the pop R2. But after we execute push R1, so we will see in the stack here, R1 is now, yeah, in this stack. And now our stack of top of stack will be here. All right. So 1A, 2A, 3A, 4A, which is from R1, now is in the stack. All right. And this is now top of the stack. All right. Again, this is F0, F1, F2, 3, 4, 5, 6, 7, F8. Yeah. This is F8. And this is exactly this. Yeah. F8. Right. And in stack is this when we push R1. Now, we want to get the data back from the stack, and we want to get this data into R2 in our case. In our program, we pop the content of the stack into R2. All right, R2 initially is 0. So when we pop the first data from the stack, means that the first 32 bit will go to R2. All right. And now see the this SP is pointed to 200000 F8, exactly this. And when we pop, right, pop this, and we get the value to R2 here, right? So 1A, 2A, 3A, 4A will go to R2, and we still, in the stack, we still have the data, right? Remember, the computer, the microprocessor, when you move the data from one place to another place, it means actually a copy process, all right? So this one is not empty actually, all right? But look at this, SP, the stack pointer is pointing to FC, the top of stack, means that the top of stack now is this one, not this one, 78. So when we pop again, right, which means this instruction, pop R2, again, it will get the data from this part, yeah, because our top of the stack is uh, FC, which is this one. So let's run. All right, so it is pop to R2. So we have R2, 1, 2, 3, 4, 5, 6, 7, 8, which is exactly this one. Okay, so that is how we use the stack, right? So now go to the next, which is the subroutine. So what is subroutine? Subroutine is again the way we write the program that we can create a subprogram in our program, and we can use that subprogram many times, just like you have a function in C programming where you can use that function many many as many times as you want, right? You just call that function when you want to use it. Same as subroutine, right? It is actually a sub program within your program. So some of the operation you may need to use it many times. For example, to read the input or to output something to the output devices. All right. So the process is actually the same. All right. So you you will not want to write that line of code again and again in your program, because it's will make your program big. All right. So when you have the part of code that you want to use many times in your program, so you need uh, uh, to make that part of code as a subroutine or subprogram that you can call it whenever you want to use it, right? So that is a subroutine. So for example, in the computer or in your program, yeah, in the computer programming, so we want to have a program running like this. This is operation 1, for example, operation 2, and at some point we want to do operation 1 again, and this operation 1 got many lines of code, yeah, again here. So the best way is that instead of you have you need to write the code again here, so the best way is to to have another part of program that you can call it OP1, and this OP1 may have many process until you get out from the OP1, all right, or what we call a return. So in this case, instead of writing all the code here, you just call OP1 here. Means that your microprocessor will go to this OP1, execute this, and then get back to the main program here and do the OP2, operation 2. And when you want to use OP1 again, you just call OP1, and your microprocessor will go to the same program, same line of code, process this until finished, and go back to the main program and continue another process until the end, right? So that is means by subroutine. So now let's look at the example. Here is another example of the programming, yeah, a more advanced programming where we use subroutine in our program. For example, in our code, we have something like this. We have this value in art0, this value in art1, and here we want to use the subroutine, and the instruction to call the subroutine is BL. In ARM microprocessor is BL, right? So this is the instruction to call the subroutine, and this subroutine is named routine1. All right. So the subroutine name can be any name. So the programmer need to name it. So in this case, subroutine routine1 is this. So you see, routine1, you can have many line of code, right? And when you want to return from subroutine back to the main program, the instruction to be used is bx. Bx. We will see later how this work. So when you call subroutine, your microprocessor will go to subroutine and execute all the instruction here. And bx means go back or exit the subroutine. So it will execute the next instruction after you call the subroutine, which is this logical shift left, and the next one, and until the end, right? So this is how this work. So BL, go to subroutine, execute all BX, and go back and execute this, right? When you want to use this subroutine again, you just BL routine1, and it will go again to this, right? So that is the idea of subroutine. But how actually the microprocessor manage this? How the microprocessor know that it need to go to this subroutine and after execute the subroutine, the microprocessor know that where to go back to the next instruction to be executed, all right, after the subroutine. So we need to use the PC, the program counter, and the LR, LR link register. Okay, again, when we go back to this, the programmer models, right, we have 15 registers, R0 until R15, and these three are special purpose register, right? The first one is stack pointer, this one is LR, the link register, and this one is PC, the program counter. So this link register and program counter is used when we execute the stack pointer, and actually the program counter is used every time the program is executed. Remember, the function of program counter is to point to the next instruction to be executed, right? So Okay, let's see how these two work together in order to execute the subroutine. All right. So the function of LR, the link register, is actually to store the return address of the subroutine. Yeah. So when you execute the subroutine, means that you need to go back after you execute the subroutine. You need to go back to the instruction after you call the subroutine. All right. So the address of the instruction to be executed next after you execute the subroutine is stored in LR, the link register. So let's see when we execute the subroutine how the computer works. And remember, the computer is hardware. So just imagine how to design a hardware that we know which one or which task to do. All right, so normal execution is to execute the instruction based on the address that is pointed by PC. But when you call the subroutine, because the subroutine is located uh, not in the sequence of the program, of the main program, it means that the program, the subroutine, is located somewhere in your memory. So the PC needs to change the sequence. Yeah, it is not count uh, in sequence anymore. It needs to jump to other location in the memory. So uh, we need to have the hardware that know what to do after we do this. Yeah, so that's why we need the LR, the link register, to store the return address. And let's see how it's work actually, right? So maybe we use this. Yeah, it's better to visualize the things. And let's see the subroutine example. All right, so this is the program, exactly the same with this one. So we have this, and we call subroutine 1 here, and this is the subroutine. And let's see when we execute this, what happened. Okay, so when we execute all of this, let's say we are here. All right, we have SP, we have stack pointer. In this case, we use stack as well. So the stack pointer is point to this because we load this value into SP, and R0 is this, R1 is this, we have this. And now the next instruction to be executed is BL, means that we want to call this subroutine or routine 1. And let's look at the value of PC. So PC in this case is pointed to this address 408. So 408, when you look at here, this is 408, and look at this arrow, the yellow arrow. All right, it is a point to 408. Yeah, 408. So this is where the PC is. Means that the instruction to be executed next is BL. This BL.W. or BL, routine 1. And our routine 1 is at address 418. All right. When we look at this, the routine 1, here we can see the first instruction for routine 1 is push. So this one. This is the address of our subroutine, which is 418, 41A, all are in routine 1. So you see the address for subroutine is now not in the main area of the program, right? So after we execute the BL, the next instruction to be executed is LSL, or logical shift left, which is this one. All right. And the address of the next instruction to be executed is 40C. So we need to keep this 40C somewhere such that after we execute the subroutine, we can get back to this. All right. So that is why we need to keep this in the LR register. Right. So let's see the LR register. Initially, we have this, which don't have the meaning yet. Right. PC is 40408, which is this one to be executed. And now we execute and see what happened. When we execute, press this. See the arrow is the yellow arrow is jump to the subroutine. And the next instruction to be executed is now 418. PC is 418. And now the address of the instruction to be executed is stored in LR, which is 40D. All right. So in ARM microprocessor, the address, the written address actually is 40C, but it says 40D plus 1. 40C plus 1. Always like that. All right. When we want to return, it will return 40D minus 1 into PC. We will see later. Right. And we can see that when we execute the program in subroutine, okay, it will execute all the program in the subroutine. You push now push already. So we have this. Execute again. Where are we? Sub, this one, sub. Yeah, we do this one. Yeah, this one. Next, we want to pop. Next. Now, here, BX. We are at the end of subroutine already. We want to return BXLR. BXLR. This one is to return. All right. Means when we want to return, this value need to retrieve or put in PC. All right, so that we can go back to 40C. This value minus 1, 40D minus 1, and okay, let's execute 40C now in PC. See, 40C, 40C. And now the microprocessor will execute this one because the PC is pointed to 40C. Execute this, we have this, execute this, and the instruction after that until finish. Right? So that is how the microprocessor execute the subroutine. It is not straightforward inside the microprocessor. We as a programmer, although actually we no need to control that, but the circuitry inside the microprocessor will do that job for us. But we need to understand how the microprocessor execute the subroutine and what going on in the hardware level. All right. So when we go back to this and let's see what happened actually. So this is the value. For example, before we start or execute the subroutine, our instruction is point to our PC is pointed to the address of the instruction to be executed. And let's say, for example, the instruction to be executed is 408, which is the BL instruction. And when we execute the BL instruction, the return address will be stored in the link register LR, which in this case is 40D, which is the return address plus 1. And the PC will now point it to the instruction, the first instruction of the subroutine 418, right? And we run the instruction in the subroutine until finished. And when we execute the LR instruction, the value of this -1 and load back into the PC 40C, such that we can get back to the instruction after we call the subroutine. All right. So any question? Okay, so this is a little bit tricky, but you need to understand this. So if you can understand this, you will understand how the microprocessor work, how the microprocessor execute the instruction, execute the program that you write, and now we look at another example. What if we have many subroutine, and in subroutine we can what happen when we call another subroutine inside a subroutine? Okay, for example, this is the program, this is the main loop, and this program we call the subroutine here, go to routine 1, and of course when you call routine 1, the microprocessor will go to routine 1 and execute this instruction, this instruction, this instruction, and again in this routine 1 you have another subroutine call. All right, you call the second subroutine inside routine 1 here, call routine 1, routine 2 here, and of course when you call routine 2, the microprocessor will go to routine 2 and execute instruction in routine 2 until finish and go back. The question now is, here we have only one location for storing the return address, which is the link register or LR. All right, link register. So when we execute two subroutine, or we call subroutine from a subroutine, all right. So what happened is that, for example, the address of the first subroutine, routine 1, the address is 10. Routine 2, the address is 20. Okay, this is the address. And let's say this is your program, main program. You have many lines of code, and you call the subroutine BL routine 1 here, and the address of BL is for example 5, and let's, for example, The next instruction to be executed is at address 6, right? The next instruction, for example, MOV or any instruction 6, yeah. And for the routine one, you call BL. So let's, for example, the BL instruction is at address 11, and the instruction after that, move or add, is at location 12. Now, how the microprocessor execute this? So remember, we have PC and LR. First, you need the PC program counter, and the second one is the LR. And let's see what happened. So when we are here, yeah, the execution, the instruction to be executed is this. We want to execute this BL routine 1, means that we want to call this routine 1. So of course the value in PC is 5. Yeah, it is point to this instruction. Okay, so when we execute this instruction, the PC will be replaced with the address of the subroutine, which is 10. And the return address is now, this is the return address. We need to save this return address such that our microprocessor can get back to this address after execute this. So we need to save in the LR register. So 6 will go to LR register. And remember, in our microprocessor, the return address is plus with 1. So the return address will be 7, right? So this is in ARM microprocessor. Yeah, in other microprocessor, normally there is no plus 1. All right, but in ARM microprocessor, the return address is plus 1. LR plus 6 plus 1, we have 7. Okay. Now this is okay. So far, so good. No problem. Now the microprocessor will execute this. Done. Go to this routine. That one will be the first instruction may be move. Now this one is executed. And the next instruction to be executed will be 11. All right. Now the microprocessor want to execute this. When we execute this, because this is BL, another BL instruction, so the PC will need to be loaded with the new value, which is not 12, but this 20. And again, the return address here will be the return address. All right. So this return address again need to be saved in LR. And this is done automatically. But remember, our LR is now has this, right? We have this in LR. And if we execute BL, this 1, 2 will automatically replace the value here. Number 7 here, or 1, 2 plus 1, remember? So you have 1, 3. And this number 7, the previous value, will be lost forever when you do that. And the microprocessor will not be able to come back to this again. And your program will be corrupted, right? Because of this. So when you execute a subroutine in a subroutine, you need to be careful, all right? But actually it can be done by saving this. Yeah, before we execute or after we execute this instruction, the first thing we need to do is to save the value of the previous LR, which is 7, in somewhere, right? So that you can get it back when you want to go back to this. So this is another application of stack, where you can save this value in the stack. Then when we want to use, you can get back from the stack. All right. So that is why when you have a subroutine like this, and you want to call a subroutine, another subroutine inside a subroutine, you need to save the LR or the return address in the stack first, so that you can use another BL in this subroutine. If not, you will lose the value of return address forever, right? So what you do is actually this. Instead of you call the second subroutine here, so what you need to do is, in routine 1, before you run the BL instruction, okay, again, let's go back to the first, when we call the first subroutine. All right, our PC is pointed to number 5 to be executed. So 5 PC. When we execute this, the PC will point to the instruction in the subroutine 1, which is number 10. And the return address here is this 6 plus 1, which is 7. All right. But because we write the program, we know that we want to call another subroutine in this subroutine. So before you do anything here, you need to keep the return address in the stack. So you can use push LR, so that this number 7 will go to the stack. So we have the stack here. It will be stored safely in the stack when you run it here. And when you call the subroutine, the second subroutine, BL, so the PC will point to the address of the subroutine, the first instruction of the subroutine 2, which is 20. And of course, the return address will be stored in the LR, which is 1, 2 plus 1, which is 13. Right? And in subroutine 2, you may have instruction until you have B PX on the return, right? LR, so that even get the value of this, put it back in PC, and again it should be -1, which is 1 2 1 2. All right, and it can execute this, execute the next, and you need, when you want to return back to the main program, what you need to do is you pop LR and the value from the stack into LR. So the value in stack is 7. When you pop to LR, it will automatically -1. So you have 6. Yeah, 7 here, go to LR -1. You have 6. And the microprocessor now know already, after this, is need to go back to here, number 6. Because the PC will, sorry, LR is still 7 and PC will be 6. Yeah, when you pop from here to LR, no need to pop to LR, sorry, pop to PC. BX, this is okay. This is wrong. We pop to PC, yeah. The LR is still the same, so we pop 7 to PC, so PC will have 6, and we get this. Right? So that is how. So let's see, this is the program. Yeah, we call BL routine 1, and here you see we save the return address, which is the address of this one. We save in the LR in the stack, because the return address, when you use BL instruction, it will save automatically in LR, and we need to save that value in the stack. And we do run any instruction here, right, that we want to do. And when we call routine number 2 here, and the LR will be loaded with the new return address, which is this address, and the PC will be loaded in with the address of routine 2, which is this one. And when we BXLR here, it will go back to this, and when you pop PC here, it will go back to this and run the next one, right? So that is how the microprocessor work. And we can see that process in Kill, actually. Okay, let's see. When we run in Kill, what happened to that? Okay, so this is a program, and let's run. So this is the program, and let's say we run this one up to here, so we can run up to here. And now the instruction to be executed is the BL instruction. Yeah, I look at the yellow arrow here, BL, and the value in PC is 408, which is this one, to be executed. And when we execute this instruction, the BL instruction here, so what happened is that the PC will be replaced by the address of this, which is 418, actually, because we branched or call 418 here. When we look here, 418 is this push LR, exactly this one, right? And let's execute this. When you execute, it will see jump to this location 418, and in our PC is 418. And the return address is now in the LR, and which is 40D, right? -1, which is 40C. The next instruction to be executed after we execute BL is this MOV, right? So this is 40C. +1 is 40D, right? Now the microprocessor will execute the instruction in the routine 1, and the first instruction to be executed is push LR, means that we save this value in the stack and try to run this. Where is it? The arrow. Oh, this is again. Okay, execute this. Oh, sorry. Stop first. Reset. Run again. I accidentally pressed the wrong one. So execute 408, and we execute this one. We want to execute this 418, and we want to push LR into the stack. And we push. So now the stack pointer, see, look, FC, it will point to FC here, because this is 8, 9, A, B, C, and this is 40D. Yeah, the value of LR is now in the stack safely, and we can execute the instruction here. Execute until we want to call the next one, BL, and the next one is the location of the subroutine number 2 is 426. All right, 426 means that the PC will be loaded with 426, and LR is the return address, which is 424 plus 1, which is 425. Yeah, we expect that. Execute. Yes, LR, we have 425, the return address, and the PC is pointed to 426, which is this 426, right? And we execute. It will do this the instruction in the routine 2. Yeah, do this until we BX. Right? Now we want to BX, want to return. So return, it will get the return address from the LR, which is 425 minus 1, which is 424. So we go back to 424, which is this one. Okay, see, we have PC 424. So we go back. Now we want to pop the return address from the stack to the PC, so that we can go back to this, right? 42, which is 40D minus 1 is 40C. We want to go back to 40C, which is this, yeah, after we call the first subroutine. So let's execute and see. All right, yes, we get the 40C from this. We get this, and we can now go back to the instruction just after we call the subroutine, which is this one, and we execute the next until finish, right? So that is how the microprocessor execute the subroutine. So with this method, you can call a subroutine inside a subroutine, or maybe you can want to call another subroutine from routine 2. You can do that. by saving the return address again in the stack, right? So that you can get back to the location that you previously or the location that you want to execute after you call the subroutine. All right. Okay. So any question regarding the stack and the subroutine before we look at this example? And then I think after this example, it's done for chapter 3, and we will do some tutorial questions, right? But before that, we will have a short break, yeah, but after this example. Okay, so let's look at this example. Now we have learned how to write the program for the microprocessor already, and the program that we write, yeah, is to manipulate the data within the processor and the memory. Yeah, means that within the resources that stay inside the microprocessor. Yeah, the data is inside the microprocessor. Now, what if we want to get the data from outside the microprocessor? Means that read from the outside, and we want to process that data, and we send back to the output devices. Okay, so that is the job of the microprocessor, right? To get the data from the outside, process, and then return back the data to the output, so that the user can see the output. Okay, so that what we will do after this in chapter the next chapter. So we will look at the detail in the next chapter, but this is the example of how we use the microprocessor, how we program the microprocessor to read the input from the outside, and the process and the send back the output to the outside. All right. So for example, we have something like this. Eh? Suppose that our ARM Cortex M3, and this ARM Cortex M3 is a microcontroller, yeah, that input and output register at address this. This is the input register, and this is output register. So what is input and output register? So in microprocessor, the input or output is actually mapped to the location in the memory. Yeah? Right? It's part of the memory actually. Okay. So in this example, the input register is this, and the output register is this. Bit number 0 and bit number 1 of the input register are connected to switch 1 and switch 2 respectively. All right, means that we have the circuit like this, and switch 1 and switch 2 is connected to the microprocessor, and this is mapped to this, yeah, at the location or at the address this address in the memory. And bit number 1 is for switch. Bit number 0 is for switch 1. Bit number 1 is for switch 2. All right. Bit number 0 is for switch 1. Bit number 1 is for switch 2. Okay. The output register is connected to 8 LEDs. Write a program to turn on the LED that are connected to the lower 4 bit of the output register when switch 1 is pressed. Meanwhile, when switch 2 is pressed, turn on the higher 4 bits, and if both are pressed, turn on all the LED. So it's like this. So when we press switch 1, the lower 4 bit will be turned on. These 4 LED will be turned on. When we press switch 2, this 4 LED will be turned on. And when we press both, all the LED will turn on, right? And the condition of the switch, whether press or not press, is represented by these 2 bits in the memory location 20001000 here. And the LED is connected to this 1010 in the memory. And this bit number 0, 1, 2, 3 is connected to this, and this is this bit number 4, 5, 6 in the memory. Now we want to write the program such that if the switch is pressed here, number 1 pressed, so this LED will turn on. So the condition of the switch is represented by the bit in this bit number 0 and bit number 1. So for input register, logic 1 indicate that the switch is pressed. Logic 0 otherwise means that not pressed. So in this case, when bit number 0 is 1, means that switch 1 is pressed. When logic here is 0, means that switch 1 is not pressed. All right, and to turn on the LED, for example, we want to turn on bit or LED 0 here, so just set this bit to 1. Now the LED is on, right? So to write the program, again, we need to have the flow chart. This is our planning. All right, so to do that, so we need to have the planning, and this is the planning. So the first thing that we need to do is to set pointer to the I/O register, input output register. So we need to set the pointer to these 2 register, because this one is the input, this one is the output. We turn off all the LED first, and we check whether switch 1 is pressed or not. If pressed, we turn on all the lower 4 LED. All right, but if not, we check switch number 2. If pressed, we turn on the upper 4 LEDs. But if not, no, we need to check whether the both switches are pressed or not. If yes, we turn on all LED, but if no press, we go back and check again, right? So when there is no switch pressed, the flow is this way. Switch 1, no press, no. Switch 2, no, nothing. Post press, no, go back, and nothing, all off. All right, but if switch 1 pressed, we need to go here and go back and check again. Still pressed, turn on, still pressed, turn on, but off again, go this way. So that is how the program should looks like, yeah. And this is the code to do that. First, we need to point to the address of the input and output register. So the input register is this, yeah. This is the input register, and this is the output register. So we store the input register in R0. The output register is in R1. Right, now we want to read the switch. But before that, we need to turn off all the LED. How to turn off all the LED? The idea is that we put all 0 here. Right? Make sure that all these bits are 0. Right? So the program is to send 0 to this location. So how to do that? All right, so now we apply what we have learned before. Okay, so for example, we use R4 here. All right, so you have many register that you can use in your program. In this case, yeah, we use R4. So we have 0 in R4 and we use this store, right? Because we want to send 0 here, here, 0. So the 0 must be in the microprocessor first and we send to the memory, right? So we need to use store. So store R4, and remember R4, we have 0 in R4, and we send to this, R1. So R1 we have this. When we send 0 to this memory location, of course we will have all 0 here, and when we have all 0 here, we will have this all off. Okay, that is easy. Now we want to read the switches. After we turn off all the LED, we want to read the switches. First, we want to read whether switch 1 is pressed or not. All right. So how to read the switch? Again, we need to get the what is inside this into microprocessor so that we can process. We can check whether it is pressed or not. Right. So the value inside this we have this. Bit number 0, 1, 2, 3, 4, 5, 6, 7. So if all bits are 0, means that the switch is not pressed. And remember, the switch is only represented by these two bits, bit number 0 and bit number 1. All right. So if inside here is this, means that switch number 1 is pressed. Okay. So what we need to do is we need to get this value into the microprocessor first. All right. So here this is how we get the value into the microprocessor. We load, right? We load and we use R2. So R0 is the input, remember? The address, what is pointed by this into R2. Now our R2 is the switch condition. And we need to do this. We end R2 is 3. What is this? This is called masking, masking process. So we want to make sure that all other bits are 0, because remember, in the memory, sometimes this one may be 1, this one may be 1. All right. So we need to make sure that all of these are 0 because we want to compare with this value. We want to compare with the value that is represented or represent the switch is switch 1 is pressed. So when switch 1 is pressed, the only value that represent that condition is this. All right. So we need to compare with this number. Compare with 1. 1 means switch 1 is pressed. Yeah, but before that we need to make sure that this one, this 2-bit, other than this 2-bit must be 0. That's why we need to end with number 3. All right. So to end with number 3 means that we end with this. So we will have 0, 0, 0, 0, 0, 0, 0, 1. Okay, we want to preserve these 2, and the others we want to make sure that it is 0 so that we can compare with 1 later on. Right? So this is how we do. Yeah, we must we compare the things, the value that we read from the input with number 3, and we save the value in R3, and we compare R3 with 1. All right. If it is equal, means that switch 1 is pressed. All right, because the value is 1. If the switch 1 is pressed, we use BEQ, branch if equal. Right? If the value in R3 is equal to 1, means that the switch is pressed, then we go to switch 1. So this is switch 1. So what we want to do when switch 1 is pressed, turn on all 4 LEDs. Right? 4 LEDs, lower 4 LEDs. So this is how we move this and 0F. So 0F is in 8-bit is 0, 0, 0, 0, 1, 1, 1, 1. All right. So when we have this and we send to the output register, which is R1, then the LED will turn on. This LED will turn on. And we go back to this label, B read. Go back to this label, read again. All right. Exactly this. When we turn on, after we turn on, we go back and read again. Now we read again and see the switch is still pressed or not. Test again, read, get the value, mask, compare with 1, and it's still pressed. You go to switch 1, do this, on 4 LED, and then go back. But if it is not pressed, if switch 1 is not pressed, means that the value inside R2 is not equal to 1. Means that can be other value. Maybe the switch 2 is pressed or both or not pressed. All right. So it will skip this and compare with 1, 0 or 2. When you compare with 2, means that the switch 2, you compare whether switch 2 is pressed or not. Right? Because value 0, 0, 0, 0, 0, 0, 1, 0, which is 2, in hexadecimal. So means that we want to know whether the switch 2 is pressed or not pressed. So this is how we do. We compare with 0, 2. So if equal to 0, 2 or pressed, we go to switch 2. So this is switch 2. We move this into R4 and send to the output here, F0, yeah. F0 means 1, 1, 1, 1, 0, 0, 0, 0. This is F0. And when we send to the output, so this 4 will on. But again, if it is not pressed or not equal to 2, maybe both are pressed. So we check whether both are pressed or not. So to check whether both are pressed or not, we compare with 3. Again, because 3 is 1 1, 1 1 means both are pressed, and this is 3, right? So if equal to 3, we go to both. Both means that we on all LED. So 0 FF cross FF means that all are 1, and we again send to the output and go back to it again, right? But if not equal means that this is not pressed, and we just go back to this INI, or back to read actually at EAD. So in this case, let's see, we go back after on turn on, or if not turn on, we go back to here. If no, we go back to here means that yes, you go to INI T. Okay, so that is how we implement or apply what we have learned in practice. All right, so that will summarize what we have learned in chapter 3, and after this we will do this, and before that we will have a short break. So any question before we continue with the tutorial?